नमस्कार. तर आजच्या या व्हिडिओमध्ये आपण आयसोमेट्री म्हणजे काय हे बघणार आहोत. मागच्या व्हिडिओमध्ये आपण ऑर्थोगोनल लिनियर ट्रान्सफॉर्मेशन म्हणजे काय आणि त्याच्या प्रॉपर्टीज बघितल्या होत्या. तर आजच्या व्हिडिओमध्ये आपण आयसोमेट्री म्हणजे काय हे बघणार आहोत. तर पहिल्यांदा आपण आयसोमेट्री म्हणजे काय त्याची डेफिनेशन बघूया. लेट व्ही बी ए finite dimensional inner product space, a function alpha from phi to v is said to be isometry if norm of alpha x minus alpha y is equal to norm of x minus y for all x comma y belongs to V. That is, if the term alpha x minus alpha y and their norm is equal to x minus y. No, there are some remarks. Isometry, it means it preserves the distance, that is distance between alpha x and alpha y is equal to the distance between x y. रफली वी कॅन से दिस. रफली आपण असं म्हणू शकतो की आयसोमेट्री म्हणजे काय, तर हे जे मॅपिंग आहे ते डिस्टन्स प्रिझर्व करते. मग व्ही हे इनर प्रोडक्ट स्पेस आहे आणि एक फंक्शन डिफाईन केले, त्याला आयसोमेट्री कधी म्हणायचं, तर डिस्टन्स बिट्वीन अल्फा एक्स अँड अल्फा वाय अँड डिस्टन्स बिट्वीन एक्स वाय. नॉर्म इज युजली इव्हॅल्युएट और यूज टू calculate the distance. So first remark, an isometry is a distance preserving function. An isometry is distance preserving function. Second one, an isometry need not to be a linear. An isometry need not be a linear. Third one, every orthogonal linear transformation is an isometry because if T is orthogonal, implies norm of Tx is equal to norm of x. This implies norm of T of x minus y is equal to norm of x minus y, and as T is linear transformation, instead of this we can use T of x minus T of y is equal to norm of x minus y, and this is the nothing but the definition of isometry. So whenever we have a orthogonal linear transformation, जेव्हा T हे orthogonal linear transformation असेल तर ते isometry satisfy करते. Now we have some examples of isometry. First example, let alpha from R to R given by alpha of x is equal to x plus c, where c is fixed constant Now we have to check this is an isometry or not. Now norm of x minus y is equal to norm of x plus c minus y minus c. This is nothing but x minus y, and norm of alpha x minus alpha y is equal to or hence is equal to norm of x minus y. Here we can use we have norm of x plus c minus y minus c is equal to norm of x minus y, hence norm of alpha x minus alpha y is equal to norm of x minus y. तुम्ही दुसरी मेथड यूज करून प्रूव्ह करू शकता की दिस इज एन आइसोमेट्री. नेक्स्ट एग्जाम्पल, t from r2 to r2, t from r2 to r2 defined by t of x1 comma x2 is equal to t of x1 comma x2 is equal to t of x1 comma x2 is equal to x1 minus 2 comma x2 plus 1. Solution: let x is equal to x1 comma x2 and y is equal to y1 comma y2, both are belongs to r2. Now norm of x minus y is equal to norm of x1 comma x2 minus y1 comma y2. Now using the definition of norm, we have this is equal to square root of x1 minus y1 bracket square plus x2 minus y2 bracket square. Also t of x1 comma x2 is equal to x1 minus 2 comma x2 plus 1 and t of y1 comma y2 is equal to y1 minus 2 comma y2 plus 1. Now norm of t of x1 comma x2 minus t of y1 comma y2 is equal to norm of x1 minus 2 comma x2 plus 1 x1 minus 2 comma x2 plus 1 now t of x1 comma x2 is equal to x1 minus 2 comma x2 plus 1 minus y1 minus 2 comma y2 plus 1 and their inner product. बराबर, t of x1 comma x2 is equal to this and t of y1 comma y2 is equal to this, minus sign add as it is. So this is equal to, if we solve this, norm of x1 minus 2 minus y1 minus 2 is nothing but x1 minus y1 comma x2 plus 1 minus y2 plus 1 is nothing but x2 minus y2. So this is equal to square root of x1 minus x2 bracket square plus y1 minus y2 bracket square. This is equal to nothing but x1 x2 comma y1 y2. So T preserves the norm by this mapping, hence T is an isometry. Next example is for your practice. Beta from r cube to r cube defined by beta of x1 x2 x3 is equal to x2 upon square root of 2 plus x3 upon square root of 2 x1 comma minus x2 upon square root of 2 plus x3 upon square root of 2. You can validate this mapping is an isometry or not. Next definition is what is mean by translation. Next is what is mean by translation. So definition of translation is, let V be a finite dimensional vector space. Let V be a finite dimensional inner product space. Let V be a finite dimensional inner product space. Let V0 be a fixed vector in V. Let V0 be a fixed vector in V. A function alpha from V to V given by alpha of V is equal to V plus V0 is called translation of V. There are some remarks. First one is, every translation is isometry. Every translation is isometry. So every translation is isometry. If V0 is non-zero, then translation is never a linear transformation. If V is non-zero, then translation is never non-zero. Third one, every isometry is a composition of an orthogonal linear transformation and translation. Every isometry is a composition of an orthogonal linear transformation and translation. That is, every isometry